Hello, this is Gene Fry. I started studying climate change in 1989, shortly after I got my PhD from Cornell. It was called global warming then, it's still a good term. I worked for many years at the Massachusetts Utility Commission, most of all on evaluating savings from energy efficiency programs, but also early on assigning damage cost per ton to various pollutants, especially global climate change ones, greenhouse gases. Also worked for a few years at Western Mass Electric and Connecticut Light and Power, overseeing evaluations of savings from energy efficiency programs, more briefly at the Energy Office in Maine, and also for a couple of environmental newsletters, and very briefly for a consulting firm evaluating savings from energy efficiency. So I'd like to talk to you today about research that's been done by many people, featuring my own research on climate change. So let me move to um, the PowerPoint slideshow. Put this down here to get a little picture of me. And let me get this started. So feedbacks are something that are underappreciated. That shows us why carbon neutral is way not good enough. So the major topics to cover, fairly long introduction, then climate history, climate change drivers, focus on feedbacks, putting the feedbacks together, and then looking at climate futures using scenarios I've developed, as well as research done by other people. And finally, how we slow and stop and reverse climate change. So quick diagram, mechanics of global warming. At the bottom, humans burn fossil fuels, increases concentrations of the atmosphere, which leads to rising temperatures that thaw permafrost, which release more greenhouse gases, methane and CO2. And the warmer temperatures melt ice. Sea ice is the fastest one of those. You lose reflectivity, a process called albedo change, which results in more warming, a rise in sea level, more acid oceans, changes in currents, and here on land where we are, more severe weather patterns with all kinds of implications, most especially food and water. A key misconception that's very widespread out there: when we stop putting carbon in the air, Earth's temperature stops rising. Instead, it only stops rising when the feedbacks, mostly reflection or albedo, and water vapor have played out. This got me started. Earth has had this much CO2 in the air before, millions of years ago. It was much hotter then. This study examines the factors that threaten to make it that hot again. Now, for what got me started in 1989, I saw the maps on the next slide. Another part of that study found that US food production would fall 30 to 50% by 2059 as Earth's temperature rose more than 4 degrees Celsius. That study captured my total attention and has held it ever since. So here are the maps, one by one. It's called the Supply-Demand Drought Index. At the bottom left is once a century drought in dark brown, and at the over to the right is once a century flooding in dark green. White is more or less normal. We're looking here from 1989, first backward to 1969, 20 years in their past. You see a good bit of white area, and the green area is similar to the yellow area. Dark green is fairly similar to the orange area, a little bit dry on average. Okay, then we look 10 years in their future, which is 20 years in our past, see the patch of once a decade drought, more or less stretching from Venezuela to Korea. Let's just leave it at that. 30 years in their future, 10 years in our future, or 40 years in their future, excuse me. You see the larger patch of once a decade drought and worse, stretching from west of Mexico, even almost Easter Island, to east of the Philippines. Very broad band, covering a large fraction of the Earth's continents. Then 30 years later, with doubled CO2, 4.2 degrees Celsius warming, and more rain, especially on the Arctic, to some degree in the Antarctic as well. You're seeing once a century drought, not just from the rain, but also from the evaporation. And that once a century drought covers roughly half of most of the continents on Earth. The very rainy Arctic, helping to melt the ice there. The number 3 author is Jim Hansen, you've probably heard of. The number 1 author who presented that I saw was David Rind, part of Jim Hansen's research group. So here's the situation we're in. We're Wile E. Coyote, and we've overrun the safe zone of safe temperatures. And we're going to pay the consequences later. Overrun now, splat later. Feedbacks, mostly albedo changes, mean it will be much hotter later, unless we manage to take most of the CO2 out of the air. That's toward the end of this. Greenhouse effect you're aware of, incoming solar radiation, visible light of short wavelength is absorbed by the dark Earth, which re-radiates heat. And outgoing, shorter wavelength, some of that's intercepted on the way out by greenhouse gases, and some of that is directed back down to Earth. More greenhouse gases, warmer still. So the albedo effect, here's an illustration of a major one. Snow and ice reflect most of the incoming sunlight, and when you get rid of them, more heat is absorbed, more sunlight is absorbed by the water, which heats up. Changing a light surface, ice, to a darker one warms Earth. Changing a dark surface, like a forest, to a lighter one, grass or desert, will cool Earth. We're seeing much more of the former than the latter. Albedo effects come from changes in area, density, and color in clouds, sulfates, sea ice, snow, and land ice. Ones I'm not covering in this study: soot, there are sources, some will increase, some will decrease, and vegetation. On net, that will probably cool Earth slightly as you lose forest and have more grass and desert. There'll be increased forest in the Arctic and Antarctic, however. Greenhouse gases warms Earth's surface far above zero, that we'd be without it. Water vapor is the primary greenhouse gas as Earth warms up. Evaporation increases water in the air. This amplifies warming from other greenhouse gases and from higher albedo a lot. CO2 is the primary one that we emit. Most of that comes from fossil fuels. Coal emits about twice as much as natural gas before you account for leakage. Methane, CH4, or natural gas, does about 30% of the rest. Those are the sources, human and natural. Human sources outweigh the natural sources, and they're the other major greenhouse gases. So here's a diagram of them by wavelength. Water on the far left and the far right, major contributions. Big contribution to the left from CO2. Smaller contribution from methane, CH4, on the right, and smaller one still from ozone toward the middle. Global climate models have improved over time. Earlier ones often emitted large-scale changes in permafrost, sulfates, and clouds because they did not understand them well enough. They also often underestimated how fast Arctic sea ice would melt, and climate sensitivity, how much warmer you get for doubled CO2. They also stopped in 2100, giving the mistaken impression that climate change stops them. As things that were left out got put in, scientists said, it's worse than we thought, more than once. So a quick look at climate history and then some analysis that I've done on it. We can learn lessons from the distant past. Going back to the time of the dinosaurs, red areas are warmer than now. On the right, the blue areas have ice sheets. Antarctica starting some 30 million years ago, and the Northern Hemisphere one starting a few million years ago. Temperatures can rise suddenly, as they are now, 55 million years ago, and again 41, although they're more sudden now. And with more ice area, the temperature swings are wider, since the albedo changes between more ice and less ice are larger. You see that throughout the Antarctic ice sheet, and it's multiplied once you get the great ice sheets in the Northern Hemisphere, Greenland, Canada, etc. Here's a look at temperatures during the thermometer era. sea in blue, land in red, and the combination in green. We've seen 1.25 degrees Celsius warming in the last century. The past 12 months have been the warmest on record. The rate of warming is doubled over the last 20 years. At that rate, both will be 2 degrees above baseline in 2058, and land will get that warm in only 15 years. You've seen another version of this, the sawtooth version. This is smooth with annual averages. And the sawtooth comes from vegetation changes as leaves grow and fall. Respiration versus photosynthesis. CO2 levels are up 47% since 1750 and 40% since the thermometer record started. Methane levels are up even more. That was especially true in the 19th century with coal mining. We're well above the maximum between ice ages. Earth's surface warming rate is 7 to 30 times the previous record that I could find in the geological record. Last time CO2 hit 400 parts per million, about 4 and 14 million years ago. Earth's surface averaged 7 and 10 degrees Fahrenheit warmer than now, and seas were 165 to 135 feet higher. Kansas was hot as Las Vegas now, and Florida was mostly underwater. This past is our guide to our future. Today's CO2 level, more detail, is the highest since 14.1 to 14.5 million years ago, when we had 430 to 465 parts per million. Deep ocean then ranged from 4.6 to 6.6 degrees Celsius warmer. Seas were 25 to 40 meters higher. CO2 levels are almost as high, 357 to 405. And we passed that 405 maybe 3 years ago. 4 to 4.2 million years ago. Sea surface were about 4 degrees Celsius warmer. They varied with the millennia. Seas were higher, almost as high as 14. That means ice then had gone from almost all of Greenland, most of West Antarctica, and some in the east. 2/3 of the ice area in the west is grounded below sea level. That's why scientists are very worried about that now. But so is 2/5 in the bigger east, with 4 million square miles, 2 in the west. Sediments show East Antarctic ice then retreated hundreds of kilometers inland, as has happened before. We face big lag effects. So now look at the Vostok ice core data, which is a few hundred miles from the South Pole, the coldest place on Earth's surface. And we see that CO2, methane, and temperatures tend to go up and down together over the course of some 400,000 years. We're above the zero baseline for 1951 to 1980, as shown in 2015 with the plus. We're off chart a bit with methane and CO2 levels. The next slide uses the data on this slide. Every 10,000 years as blue dots, we're going to eliminate the time axis and plot the bottom temperature against the top in blue, CO2. There'll be another slide after that where we'll add detail and analysis using the data shown on the previous slide. There are your sources from 4 and 14 million years ago. So lessons for our future from ages ago. The Vostok ice core, baseline temperatures 1951 to 1980. Those are the blue dots, not a perfect correlation, but a fairly good one. And that covers 420 million years. On the right-hand side is a rough translation from Vostok temperature changes to global ones using a 0.6 global to polar ratio from Carolyn Snyder in 2016, a little better than the 0.5 one that was assumed earlier. So delving deeper into this, the purple line is developed the trend line for the Vostok data using CO2 only. It explains 73% of the variation, correlation about 0.86. Using the green equation yields the green line with a better correlation, more than 90%. And those are the data that we have on both CO2 concentrations and temperatures estimated for those millions of years ago. 412 parts per million of CO2 and 1860 of CH4. Climate sensitivity is the increase in global surface temperature for doubled CO2. These data are long time series, so they have long run equilibrium, not just short run climate sensitivity. 13.24 degrees Celsius at Vostok. Long run global climate sensitivity is 0.6 times that, or 8 degrees Celsius for doubled CO2. That's long run, not just the short run that some models use. So the long run estimated equilibrium temperature, 1880 baseline, start of the temperature record due to today's greenhouse gas levels, CO2 only, using that equation, and 412 parts per million CO2 is 4.8 degrees Celsius. When you add in methane, CH4, using the green equation with 1860 on the right for methane and 412 again for CO2, you're looking at 8 degrees Celsius long run equilibrium from today's greenhouse gas levels. Now, using the green one again, methane and carbon dioxide, to hold warming to 2 degrees above 1880 requires, for example, 317 parts per million of CO2 and pre-industrial levels of CH4, 694 parts per billion. This requires removing 70 to 75% of the CO2 that we've already emitted, all our future CO2 emissions, and all our methane emissions past and future. Our remaining carbon budget to hold warming to 2 degrees for burning fossil fuels is negative 310 billion tons, or gigatons, GT. Now looking where most of the heat goes, we are the tail wagging the dog. The atmosphere is the purple area just above the zero line. Almost all the warming goes into the oceans, roughly 93%. 2 to 3% goes into melting ice, and some 2% into heating up the land surface. Looking more closely at the ocean heating, that's just where almost all the heat goes. One of those marks on the left is 100 years of US energy use. These are very big numbers we're talking about. The curve grows steeper, 0.4 per year, then 0.7 per year from 1991 to 2005, now up to 1.0 per year. So 17 times human energy use goes to heat up the ocean every year. Over 3 years, that's as much heat the ocean gains as all the energy humans have cumulatively used. A lot of heat in the ocean. So the climate change drivers, we're going to focus on feedbacks. It's too neglected. So some 13 years ago, there's my first introduction to tipping points. What would make climate change accelerate so natural forces defeat our efforts to slow it? Disappearance of sea ice. We saw that diagram near the beginning. Carbon sinks fade in oceans and forests. They become carbon sources when you burn forests, for instance. Methane release from permafrost, we saw in the initial diagram, revs up warming in a vicious circle. So water vapor's greenhouse effect, that's the #1 greenhouse gas. Warmer air contains 7% more water vapor per degree. That increases radiative forcing by 1.5 watts per square meter. That's 86% as much as from CO2 we've emitted, or 45% as much from all our greenhouse gas emissions. Now the chief albedo effects: clouds, sulfates, sea ice, snow, and land ice. We'll examine each in turn. Half the sunlight reaching our atmosphere makes it to the surface. Barriers include clouds, sulfates, blue sky, backscatter, and the ozone layer. So look at clouds. Clouds are very complex. They reflect some sunlight away, cooling Earth, but they also keep outbound heat in, warming Earth, especially at night. Many factors affect them. At night and going up over mountain, air cools. Cool air holds less water, so often cloud up and rain. Clouds cover a little more than half of Earth. On balance, they cool it. Low clouds cool Earth more than they warm it. High ones do the reverse. That's important because there are changes there. cloud area, altitude, and opacity all affect global temperature. Cloud cover area is shrinking a little for warming trend. More high clouds, fewer low ones, also warming. Low clouds growing more opaque, the cooling trend. The net result is a warming trend about 10% of the total. So here's the best diagram I've seen, research that came out almost 3 years ago from Zelenka. Total in black, less area in blue, altitude changes in red, opaqueness changes in purple, little cooling trend. So the total effect is about 0.47 is estimated by Zelenka, but 0.6 is estimated by IPCC. We're not sure that the effect is greater than 0, but it seems very likely, and we're going to go with Zelenka's estimate. I will go with Zelenka's estimate. Next one is sulfates. Dark sulfates in the air block sunlight, cooling Earth. They make haze and become cloud condensation nuclei. So you get more sulfates, it becomes cloudier and cooler. That prevailed in the second half of the 20th century in the eastern United States. Most sulfates come from burning coal, some from volcanoes, some from small sea creatures as dimethyl sulfide. Greenhouse gases stay in the air many years. Sulfates fall out after a few days. Sulfate levels are not currently rising. They rose till 1973 and 79. They fell a bit since then. So they're now only offsetting 30% of warming instead of 40. When you get rid of them, they'll offset 0. As we stop sending up sulfur dioxide, warming will catch up. So, analysis of global temperatures with sulfates. Why don't global temperatures rise smoothly as CO2 emissions did? Sulfate cooling unsmooths global warming. These are NASA's land surface temperatures. And we can see clearly effects of volcanoes. The biggest one was Krakatoa, which cooled Earth's surface for several years. There are 3 in the Caribbean, Central America, Santa Maria, 2 others, Katmai, and also one in Kamchatka. Our sulfur emissions went through the roof when we built a lot of coal plants from 1940 to 1970. That cooled things off. When you start scrubbing the sulfur out, warming was unmasked. Sulfur emissions are down 23% from their peak, but they're still triple the natural levels in 1880. There's the equation I developed. Sulfur, methane, and CO2. It explains almost all of the warming, 98%. They're all highly significant. What we see here is from the bottom, Krakatoa trough, to now, there's 1.8 degrees Celsius warming. That's almost as much as the 2-degree target. Next, moving to sea ice, especially northern sea ice or Arctic sea ice. The volume is decreasing faster than the area because the ice is getting thinner also. And what's happening as the ice recedes, shown in our original diagram, Earth absorbs more heat. Its surface will warm more, even without more CO2. Here are a couple pictures before and after of how much sea ice is there. There's still a lot left, but it's shrunk by a good bit from 5.5 to a little less than 3 million square kilometers. So here's looking at the volume and by monthly instead of annual minima. Annual minima is the magenta line at the bottom. This suggests that we can have ice-free days this decade, ice-free summers next decade, or at least by the 2040s, and ice-free for the whole year. April is ice minimum month before the end of the century. So how does that affect temperature? Hudson in 2011 estimated that total Arctic sea ice loss would warm Earth's surface by 0.7 watts per square meter, of which 0.1 had already occurred. Antarctic sea ice covers a similar area, but it's not clear that loss has begun yet. Record high ice levels, followed by record lows. This year so far is below average, but not record low. Moving on to snow. From 1982 to 2013, radiative cooling from northern snow cover decreased by 0.33 watts per square meter per degree Celsius due to earlier snow melt. 12% added to global warming from greenhouse gases. Looking at the area, it's not just the timing change. How do days of snow cover change as Earth warms up? They fall. Contrast Winnipeg with many snow days in New Orleans, never seen it. Using data for US and Canadian cities shows the extent of northern snow cover I found decreases 9% per degree of global surface warming. That's my own research a couple of years ago. I'll spare you the tables that are derived from that. Land ice is the next one, very important for sea level, but not very important for temperature change. Greenland's net ice melt rate rose 7 times, and it passed US water use. Antarctica, half as much ice, its ice loss rate tripled. That means both have been accelerating about 12% a year over that time frame, those time frames. I project future land ice loss using S-curves. Land ice area decreases far more slowly than sea ice area because land ice is so thick. So its albedo change effect is much slower, very little effect so far. Now, we're going to put these feedbacks together, looking at the past 45 years and the future out to 2400. An estimated 39% of warming over those 42 years came from albedo or reflectivity changes, both direct and indirect. Direct is in the second column, indirect is in the third column, and the total degrees Celsius is over on the right. Total's 0.33, which is part of the 0.839 observed over those 41 years. That works out to 39%. So warming in the future, especially beyond 2100, will be dominated by albedo changes and their feedbacks. The most important so far has been sulfate loss, followed by snow cover timing change, and then Arctic sea ice loss. Sulfate loss is about a quarter done. Sea ice loss is about a seventh done in the north and not done at all in the south. Snow cover timing change is somewhat done. Land ice loss is just beginning. So I distribute these warming factors to water, vapor, and clouds. You got a little bit different picture. Part of what's attributed to CO2, methane, etc., is actually more water vapor and various cloud changes. Dividing those out, we got an estimated 36% from more water vapor, 17 CO2, 12% sulfate, 11% cloud changes, 10% methane, 6% snow, 6%, a little bit less actually, for other greenhouse gases, ditto for snow melt, 3% for sea ice so far. That works out to water vapor 36, our greenhouse gas emissions 32, and albedo changes also 32%. Then permafrost. The rest don't change what's the amount of greenhouse gases in the air, but thawing permafrost does. It has about twice the amount of carbon in the atmosphere. Still in the early stages of understanding that. They're probably comparable to US transportation, about 0.6 billion tons a year. This is the best I've seen so far, and the first I've seen from McDougall some 7, almost 8 years ago. Permafrost starts out in the red line on the left in carbon in the permafrost, and it gradually goes in the air, which is the light blue line, depending on the scenario. And the temperature effect might be anywhere from 0.2 to 1.6 degrees Celsius, depending on how sensitive you think the climate is, how fast we do our emissions, and other factors. So the impacts of all these factors, the 5 albedo ones and permafrost, will continue into the future, and they'll be much greater in the future until Earth's ice and snow are gone, after which the impacts of those factors are less, and climate will be much less sensitive to doubled CO2. So Earth will warm 3 to 4 times more even if we stop emitting now. You can blame phasing out coal sulfur emissions, almost 0.4 degrees C. vanishing northern sea ice about 0.4, receding northern snow cover about 0.4, vanishing southern sea ice about the same, permafrost, etc., about the same. That's poorly known. That also includes methane hydrates, warmer soils and ocean, more respiration in soils. Greenhouse gases are less soluble in warmer water. And you've also got land ice. It's only to 2,400. Most of it happens after then. Ditto for warming the oceans enough so they restratify and will keep warming the air. Current estimate is about 0.6 to 0.8 degrees Celsius once everything is played out in the oceans. And more water vapor and less cloud cover, almost 1.7 times as much. So you put those together and you're looking at about 4 degrees Celsius warming, almost that. If carbon emissions don't peak until 2035, instead of quitting cold turkey, you can add quite a lot more warming. 1.6 from CO2, 0.9 snow, 1 from permafrost, etc., 0.8 from water vapor, and 0.4 from other factors, including clouds, land ice, etc. That's happening twice. That's twice the heating from stopping emissions now. Moreover, in this case, warming continues long after 2400 instead of playing out by now. So look at climate futures, what happens at various temperatures, and what our paths are to get there. So this is what happens at 2 degrees, drawn from the Stern Review that's about the time as the first tipping point report. We cannot avoid this. We're already in it. Hurricane costs double, many more major floods, heat waves, forest fires. We're seeing a lot in the US, Canada, especially in Siberia, and also in tropical forests, droughts, deserts, water wars. Crop yields rise nowhere and fall in the tropics. Greenland ice cap collapse is irreversible. Perhaps also true for West Antarctica. Ocean rise speeds up. So here are 6 scenarios I developed, which will play out for greenhouse gas levels, temperatures, and sea level. Sea level is the most fuzziest. I don't feel very confident in my projections. So XFS means phase out fossil fuels. CDR is carbon dioxide removal. So soil carbon loss since 10,000 BC was 60% of fossil fuel emissions till then, about 40% of fossil fuel emissions to now. So if we can remove half of that, which is probably the best you can do with rebuilding soil carbon, because half the soil is gone, eroded away. And that's the CDR case in blue. And if you can do twice that much with a lot of other methods besides restoring soil carbon, you get the green curve. So here's how that translates to CO2 levels. That's not just our own emissions. Those are also the natural emissions. We've revved up permafrost, soil carbon emissions, emissions from the ocean as the ocean surface grows warmer and gases are less soluble, methane hydrates, and other things. A lot of the increase that you see, especially in the cases where we emit more CO2, comes from all those feedbacks. Even if we cut fossil fuels by 2050, they're significant, and they increase the CO2 levels from about 500 to a bit over 700. To have much hope, really, of holding CO2 to reasonable levels, we need to take a lot out. So here's a look at 3 degrees warming. How does that translate into in terms of damages? That's very difficult to avoid, but it might be possible with massive CO2 removal as soon as possible. By mid-century, get most of it gone. Droughts and hurricanes worse, hydropower, water is scarce, crops fall substantially in many areas, more water wars and failed states, terrorists multiply. 2/3 of Amazon rainforest may turn to savanna and desert scrub. We may have already passed the threshold for that tipping point. according to Antonio Nobre, Brazil's leading climate expert. Tropical diseases spread, and a lot of species face extinction. The extinction rate now for mammals is a few hundred times the background rate already. So looking out now just to 2400 shortly, global land surface temperature, if we quit cold turkey, no more sulfur coming from burning coal, and you see a spike up in temperatures about 0.4 degrees Celsius as soon as that manages to happen. But we're better off in the out years by 2100. There's not much difference depending on what we do, 2050 to 2060, even 2070, but you're starting to see appreciable differences by the time you get to 2100. So what happens at 4 degrees, where several of those are? These are further damages, and they're avoidable if we stop putting carbon in the air very soon and take lots of it out also soon. Water shortages afflict almost everyone. Crop yields fall everywhere. Some regions, such as Australia, end agriculture altogether. Water wars, refugee crises, terrorism become intense. Methane release from permafrost accelerates. Gulf Stream and the Atlantic meridional overturning circulation may stop. It's already been slowing 15% or more since middle of the 20th century. And the ice sheet collapse speeds up. West Antarctica is the one which may collapse the fastest. How does that translate to temperatures? Well, it's not a good story. So the cases at the top is where we wait to peak. We keep on growing our emissions for a while. Below that is where we peak now or a little bit in the past, phasing out fossil fuels by 2050 in orange. So there's a Paris target and the level where Kansas gets hot as Las Vegas now. Unless we quit cold turkey, really, and do major CO2 removal, we're looking at Kansas getting as hot as Las Vegas. This includes the big albedo effects we've been talking about, loss of sulfates and sea ice, north and south, and loss of much snow and cloud cover and land ice. In the black and brown cases, probably about all the snow. Land ice still going on for many centuries thereafter. And in all cases, there's more water vapor in the air. So what are the damages? Well, these are my own estimates based on what the Stern Review had for 2, 3, and 4 degrees. Deserts grow by twice the size of the United States. Forests grow only by the size of the United States in Antarctica and Greenland. World food falls by 1/3 to 1/2. Human population falls a lot to match the reduced food supply. Other species fare worse. Extinction rates go through the roof. And that's just at 5 degrees. 5 degrees, my guess is that would collapse civilization. 10 degrees, a little bit higher than what you saw in the previous graph, threatens extinction. Now, here are my guesses, slightly informed about sea level. The 6 cases, the most emissions in the black corresponds with the greatest sea level rise. They're probably a bit too fast after 2100 or 2200. But anyway, there's a sea level that would put those places mostly underwater. This includes thermal expansion of the ocean and ice loss almost complete in West Antarctica, mostly complete in Greenland, and significant in East Antarctica. The ice loss is much less in the cases where you're doing active CO2 removal. As an economist, I would say the present value of future damages from global warming is likely to exceed the gross world product, which is approaching $100 trillion a year, by several times over if we continue business as usual. How do you value the extinction of our species? It's tough to do. Okay, now what we need to do to prevent all this bad stuff. The solutions are 2. Stop putting carbon in the air and take it out. 3/4 of what we've added so far plus any future emissions. The sooner the better. We're in a precarious position, so we'll probably need to do solar radiation management as well. Sulfates in the stratosphere, brightening Arctic sea ice, brightening clouds, solar screens in space, etc. But the solutions, our family solution, the policy solutions, technology for stop putting carbon in the air, and technology for taking it out, or natural solutions for taking it out. What we've done at our house, we have a heat pump, an electric car, 100% green electricity, which we've had for a couple decades, community solar, so it's actually more than 100%, and CO2 removal, $46 to Blue Indigo to put carbon into soil, and $32 to Climeworks to turn it into stone in basalt formations. The result is we've decreased our carbon footprint by 80%. Now, on the policy end, the obvious solution, the only one that really works, is taxing carbon across fossil fuels worldwide in proportion to carbon content. Impose the tax upstream, start low, rise briskly on a preset path. Return the proceeds as equal dividends to individuals is the best way to do it, and also end subsidies for fossil fuels. That's the world leading economist the month before the Paris Agreement. America's leading economists, all our Nobel Prize winners but one, all living Fed chairman, ex-Fed chairman, Council of Economic Advisors, etc., agreed about the carbon tax. Citizen Climate Lobby, there are 170,000 of us volunteers, proposes $15 per ton of CO2 to start, rising 10%, $10 per ton per year. Our proposal is now in Congress, first in 2018, now back again, this time with 80 co-sponsors. Includes a border tariff adjustment, differences between our carbon price and other nations. Right now it's much higher in Europe than it is here. Economic analysis shows that CCL's carbon fee and dividend path creates jobs and grows the economy. 70% of Americans receive more in dividends than they pay in higher costs, mostly for energy. It's a especially good deal for low-income Americans who don't use much energy, don't use much carbon. Emissions fall 50% in 20 years, and it saves lives. My proposal to add to that is to pay for verified CO2 removal at the same price as CO2 emissions. Personally, we're already paying to do that. Okay, good news. The cost of renewable, carbon-free, renewable energy has been falling. It's been falling for many years, and solar and wind are now the cheapest in most of the US. They're cheaper than new gas-fired combined cycle plants, and they're also cheaper than continuing to operate coal-fired plants. Therefore, their share of electric generation is rising. And the major sources, coal has been declining for 30 years, and especially steeply under Trump. Renewables have been growing substantially since about 2010. Nuclear has been pretty constant. Natural gas has been growing a lot to take the rest of the slack from coal. Now, the smaller sources, wind has been growing rapidly since 2003 and solar since 2013. Hydro is up and down, wood is about constant, other renewables are also about constant, a bit less than wood, and oil's been shrinking. Okay, now to transportation, which is now the biggest use of fossil fuels in the United States. Battery prices have been falling steeply, and car prices will continue falling as battery prices fall, making electric vehicles cheaper than petroleum-powered ones in the next few years. Their variable costs are already significantly lower. So people are not going to be buying petroleum-powered cars after 2030. As a result, oil use will fall very considerably, and oil company revenues will plummet as the price of oil falls as well. What about other uses in transportation? And aside from transportation, industrial processes, a big chunk, space heating, water heating, ships, airplanes. That's why we price CO2. Innovators will figure out ways to cut emissions. Over 10 to 30 years, emissions from the first three can be eliminated easily using electricity. Deep cuts for the latter two can come from wind, nuclear, biofuels, efficiency, and fast trains. Okay, for the most important part of all, taking carbon out of the air, focus on biology first. Farming can put away about 12% of current emissions in soils, rebuilding soil carbon content. Organic farming is the gold standard, use of no-till and compost cover being the key. We can rebuild soil organic matter to what it was before farming. Second proposal is to farm the oceans. This particular version of Farm the Oceans comes from my college colleague back in the 60s. Harvest the algae, turn them into biochar, and sink them. Other proposals involve open ocean with iron fertilization, mangroves, kelp, seagrass. Biochar is wonderful stuff. It stays in the soil for eons and holds water. It's a fairly nice fertilizer. We can rebuild rangelands with perennial grasses, short rotation cattle grazing, holistic management. Problem is, cows burp methane, but you feed them aspergensis and it cuts their burp methane levels down dramatically. Trees are wonderful. I love forests. I hike in them a lot, but warming will dry out soils. Forest fires will run wild. We've seen that in Colorado, California, Washington recently. It's even worse in Siberia, and you hear a lot about it in Indonesia, terrible haze, and forest fires turn the sky black in Sao Paulo, Brazil. Taking carbon out of the air, non-biological, this needs to play out a bit later because direct air capture generally requires more energy to operate than we got from putting carbon in the air in the first place. Costs will be falling over time. Pipe it underground or add it to concrete. Underground in basalt, especially good, turns into carbonate rock for millions of years very quickly. Speed up rock weathering, again, by attaching CO2 to rock, be more carbonate. You can sow dust across the tropics for cheaply. You can decrease ocean acidity with bicarbonates by spreading olivine gravel or dust on the surface. You can add olivine gravel to soils, which is the complement to biochar, restoring nutrients. Thing with soils is that soil respiration increases as soil warms, so you've got a window of not many decades to put carbon in soil. And you probably need to do that, and then as you get 100% green electricity, you'll be moving more to non-biological methods. So to sum up, we need to go carbon negative big time. That is the largest industry on earth is CO2 removal by 2050. Contact me for details. That website has 19 web pages with over 11,000 articles and somewhat less than 2,000 diagrams. I recommend it to you highly. www.globalwarming-sowhat.com. Thank you for your time.